Hello everyone and welcome to Module 10. So this is the week we start talking about generalized linear mixed models, GLMMs, a very fancy word for models that explain outcomes that are not continuous. So this really expands our skill set as modelers and allows us to think about modeling outcomes that really kind of expands the possibilities beyond really anything we've talked about before, which is very cool. So let's dive in. So I think it's pretty clear that many of the outcomes that we care about in social sciences and education, social work, public policy are non-normal. So they might be binary or dichotomous, right? Yes or no. They might be categorical. They might be a count, the number of times something happened. They might be scores on a scale from 1 to 7. They might be heavily skewed or censored. They might be truncated, which means they're cut off, or we might have some sort of a time factor. And all these are situations where the typical assumptions that we make that an outcome are continuous don't hold particularly well. But luckily, generalized linear mixed models, GLMMs, allow us to tackle those each pretty flexibly, which is great. So for this week, we're going to focus on this top left category, which is binary or dichotomous outcomes. But keep in mind that other possibilities are there for other types of outcomes as well. But like I said, right now we're talking about outcomes that are primarily binary or dichotomous. All right, so let's get into GLMMs. So last week we finished up our discussion of growth modeling. So we looked at the concept of nonlinear growth and how to account for repeated measures using fancy variance structures. So we really kind of looked at how the multi-level modeling framework could be extended to account for situations where things don't always meet what we would expect in terms of how our outcome is functioning. So this week we're going to jump into how to model totally different kinds of outcomes, which are categorical outcomes. And I will say, this could be its own class. Like we could have our whole class just on GLMMs, and each week, just like we've done a module here, we could do a different kind of module. So we could do survival analysis, we could do count analysis, we could do time series analysis, we could do multinomial, we could do ordered categorical, we could do logistic. There are just so many different kinds of models and distributions. But for now, we're going to look at one of the most functional and one of the sort of basic, essential generalized situations, which is a dichotomous outcome or a binary outcome. And to do that, we're going to use what's called multi-level logistic regression. I think this is probably the most common type of generalized model. And the generalized part just means that we're looking at something that doesn't conform to an underlying normal distribution. So when people talk about generalized, that doesn't just mean logistic. It could mean lots of different things, but that's particularly what we mean. All right, so let's talk more specifically about multi-level logistic regression. And to do that, we should probably talk a little bit about what regular logistic regression is. I'm assuming you've had some exposure to this in a previous course, perhaps an intro statistics course or multivariate statistics course. If you haven't, that's quite all right. We'll try to catch you up as best we can. So logistic regression is used when you want to analyze a binary categorical outcome. In this case, binary, although there also is what's called ordered logistic regression when you have an ordinal outcome. So we're talking here about binary distinctions. So win, lose, pass, fail, prepared, unprepared, vote yes, vote no, drop in, stay out. I got that backwards. Drop out, stay in. We're going to look at, in the demonstration video, we're going to look at whether or not a child has asthma. So yes, child has asthma. No, child does not. That's what we mean by a binary outcome. If you have more categories, you can extend this framework and look at ordered, logistic, or multinomial logistic regression. So that would be, for example, if you had drop in, stay in, graduate, drop out, stay in, graduate, or a scale like not at all, somewhat, very much. So it's very flexible for a lot of things. So typically, so when would you use logistic regression? Well, you would use logistic regression when you have an outcome like that you're interested in, when you have a categorical outcome. And then you have a set of predictors, and you want to know the relationship between your predictors and that categorical outcome. Very much like regular regression, where you have a continuous outcome and a set of predictors. Here, you want to know, are these variables related to this outcome? And if so, how? How do they change, in this case, the odds of something happening, the odds of a particular outcome? That's kind of a context in which you would use logistic regression. So you may ask, why do we have to completely change the type of setup? Why can't we use a linear multi-level model? Well, in general, and this rule applies as well when comparing logistic regression to regular multiple linear regression, which we studied earlier in the year, binary outcomes don't generally work very well. Many of the assumptions can be pretty seriously violated, normality, heteroscedasticity, linearity. We'll talk about some of those assumptions next week. Those are also very similar to the assumptions of regular regression. And you also often get predictions that are impossible. So, someone might have like a probability of something happening that's 200%, and you can't have a 200% probability, right? Probability only goes from 0 to 1. 0 is impossible, 1 is certain. And so that can be really challenging too. But probably the most important reason why is that for the most part, data that are binary are coming from a different underlying non-normal process. So the distribution that creates those outcomes is fundamentally non-normal, something like a binomial distribution, or at least the way in which we try to model those kinds of outcomes are different. And so it just makes sense to sort of line everything up from the distribution to the model to the interpretations. All right, so logistic regression is kind of the basic method by which we can make predictions for binary or categorical outcomes. The prediction, of course, is whether or not something happens or not, ready versus not ready. It's no longer a prediction along a spectrum or a continuum, and that's different from continuous outcomes. So to do this, logistic regression is built on this concept of odds. So odds are fundamental to the idea of logistic regression. And if you've ever played or watched something like poker or a card game that involves betting, odds are a big part of that, right? So the odds of something happening versus not happening. So odds are the probability that something will occur divided by the probability that it won't. And it's sometimes written as like 3 to 1, 5 to 1, something like that. So VCU is a 2 to 1 favorite against UNT this weekend. You can tell I wrote this when basketball was still being played. It's not being played yet, fingers crossed. Go Rams. So VCU is a 2 to 1 favorite against UNT this weekend. This means that the odds of VCU winning are 2 times larger than the odds of UNT winning. So that's basically what that means. So that it's basically a ratio or a probability of something happening. So if you have a binary, that should say, the probability of VCU winning is 2 times larger than the probability of UNT winning. Let me see. Let me change this. There we go. This will hopefully be fixed when you have it. The probability of VCU winning. Probability. There we go. There we go. All right, so let's fire that up again. Okay, so we're talking about odds. So if you have a binary outcome, you can construct odds. So let's say we're looking in a kindergarten classroom and we give some kind of a readiness screener that asks kids a bunch of questions about, about what they might know about their letters or sounds or different like functional activities, tying your shoes, stuff like that. So let's say 35 of 50 students in our little sample are determined to be ready. What are the odds of being ready? Okay, so the odds of being ready are the probability that a student is ready divided by the probability that the student is not ready. So in this case, we have a binary outcome. So the probability of being ready is 0.7 or 70% because 35 out of 50 students were determined to be ready. And 15 out of 50, which is 30% of students were not. And so 0.7 divided by 0.3 is 2.33. So the odds of being ready for kindergarten are about 2.33 to 1. So you have about 2 to 1 odds of being ready for kindergarten in this particular sample. So let's say you have 10 out of 50 students in the sample are determined to be ready. What are the odds of being ready? What are the odds of being not ready? And if you want to pause right now and try this on your own, go for it. So calculate the odds of being ready and calculate the odds of being not ready. All right, so the odds of being ready in this sample where 10 of 50 kids are ready. So that is the probability of being ready is 0.2. The probability of not being ready is 0.8. So that is 0.25. 0.25. So that's also read as 0.25 to 1 or 1 to 4. So those are the odds of being ready. The odds of being not ready are 40 out of 50, so that's 0.8. And the odds of being not ready are 10 out of 50, so that's 0.2, so that's 4 to 1. So 1 to 4 are the odds of being ready, 4 to 1 are the odds of not being ready. Now, do you have to be an expert in odds? No, absolutely not. But it is important just to understand this basic concept. So if you have a probability, then you can construct odds based on that probability. And so now we're going to go from odds one step further, and we're going to start talking about what are called logits or log odds. Okay? So if we just convert our binary outcome in a data set to odds, you have a couple problems. First of all, odds can be infinitely large. So you could have million to 1 odds, you could have billion to 1 odds, you could have any number as large as you want, but odds cannot go any smaller than 0. So there are no negative odds. If you calculate odds and they're negative, something was wrong in the calculation. So that's a problem for an outcome. Ideally, we want to be able to transform this categorical outcome into something that is basically or roughly continuous. And in this case, odds by itself is not great. And the scale is really not very linear, especially at very high and low probabilities. So that doesn't really get us very far in terms of a fix. So the fix is this. We start with a raw outcome that's transformed into odds, and then finally we take the natural log of those odds. So it's actually a two-step process. Now, I'm sure you're thinking, holy cow, how do I do all this? All of this happens under the hood with the software. So this is what's called a logistic link function. So this function is applied to the data and transforms the data for you. But I think it's important just conceptually to think about how you go from something that's categorical to something that is more or less roughly continuous. And that's essentially how it happens. We go from a raw outcome to odds to this concept of log odds. And of course, the last step then is to take the natural logarithm. And that's just a mathematical function that rescales our outcome. So it basically can take on any value between positive and negative infinity, which is good. That means it's essentially continuous. And that's called the logit transformation or log odds transformation. And the values that you get for the predictors of a logistic regression are logits. The units themselves are called logits. Okay, so that brings us to our logistic regression equation. So essentially, we take our outcome, we calculate the odds of that. That's this part right here. Then we take the natural log of the odds, and then we have something that's approximately linear. And so that is sometimes shortened by just saying logit, y. So this is the logistic linking function right here. This is the part that transforms the data. And then after that, it's essentially a regression, which is nice. That's something we know how to do. We know about coefficients. We know about estimates and error terms, and all those things work very well in this type of a framework. So that is the equation that we end up developing. And the rest of that works just the same way in multi-level modeling. Of course, in multi-level modeling, we would have two levels of equations, right? So this beta 0 would have another line down here. We'd have another error term for a random intercept. But other than that, it works very similarly. The other issue, which we'll get into, this level 1 error term is actually fixed to a constant value. And so this looks slightly different in a multi-level context. But otherwise, it's pretty similar. What you end up getting is our estimates that are fit to a logistic or logit distribution. I just want to show you what that looks like. So a logit distribution is pretty similar to a linear distribution in the middle of the probability values. It just starts to tail off at the extremes. And that's actually good, right? We don't want to estimate probabilities that are above or above 1 or below 0. So that actually is a good thing. But for the most part, in a lot of ways, it resembles a linear probability distribution, which is really good. Okay, so after that, I've got some examples here where I interpret log odds and then odds ratios. So we'll get into this in the examples. The default is to get logits. Those logits can be converted to odds ratios. In R, you only get logits, but I show you how to create the odds ratios from the logits. So I kind of work through these examples as well. And the videos are a little more detailed this week to sort of account for that, because there's a little bit more we have to unpack. So we've reached the end here. So this is a quick and dirty intro to how logistic regression works. Again, I don't expect you to be an expert in this, but I do think it's important to understand a little bit of the conceptual piece, right? That we have a categorical outcome. We apply a linking function, which basically transforms that categorical outcome roughly into something that is continuous that we then are able to model. And so that is the tool that we use to be able to estimate multi-level models for binary variables, which can be very, very useful. So, all right, the rest of the videos and demonstrations are ahead of you. Good luck and take care.